Okay, good morning. This is our second lecture on electromagnetism. So this lecture will continue sort of where we left off, talking about electric potentials and how to visualize this in 3 dimensions. Then we're going to contrast electric with magnetic fields, first by talking about dipole fields, and then starting to talk about how magnetic fields work, how magnets are created, and so forth. Now, we'll continue on with that next week with the sources of the magnetic field and so forth. So there's a little bit of overlap between today's lecture and last week's, and between today's lecture and next week's. As such, you're going to find that DLs will catch up with the lectures pretty quickly toward the end here. Now remember, last week we defined what we mean by electric potential. Electric potential is just the electric potential energy per unit charge. In other words, it's the potential energy divided by the charge. Now, everywhere in space where there's an electromagnetic field, you also have an electric potential, V, which is a scalar field, a function of x, y, and z everywhere. And our first goal here is to try to get a handle on how do we draw it, how do we visualize it, how do we think about it. Remember that the zero for electric potential can be defined to be anywhere. And then it's only differences in potential that really count. But normally we take V equals 0 far away from any charges, or where essentially there is no field. The electric field is the gradient of the potential. So there's only an electric field if the potential is changing as a function of position. If there's a slope to it, in other words. So you could think of it just like a mountain slope. Now, here's a picture that we were dealing with last week. We have one electric plate of a capacitor charged up to positive charge, the other one with equal and opposite negative charge. And we'll set that to 0 potential, V equals 0. And this one has potential V. So that creates a uniform electric field in between the plates, all pointing, in this case, in the left direction. Now, if we take a positive test charge and put it here, there's a force on it, Q times the electric field, which we write down as a vector. If that charge goes all the way from the positive side to the negative side, that's a distance d, then the work that that field does, the force on it, is Q times E times d. Q times E is the force times distance is the work, and that's equal to Q times V, because that's the total amount of work. The work divided by the charge is the change in electric potential. So therefore, we can write down that E, the electric field, is the voltage difference across this capacitor divided by the distance. So if you have 10 volts over here, 0 volts on the other side, and it's 1 meter, that would be a 10 volt per meter electric field. That's not a very large electric field. Also remember that our fundamental definition of electric field, which is in terms of force per unit charge, newtons per coulomb, is the same as volts per meter. And this is, in terms of the units, what connects the electric units to the mechanical type units we've been dealing with. So that's a reminder. And that was the thing I told you in last week's lecture, is the thing you should mainly remember from it. And you'll use that. So let's do a clicker question. See if we've mastered this. So now in this case, you have a negative charge, and it moves in a uniform field, just like on the previous slide. And it goes from 0 potential, from the left side on the previous slide, to a place where it is plus 50 volts. Now, which is true? The charge gains kinetic energy doing this? Or B, it takes work to move the charge against the field. In other words, you have to push on it. Or C, the charge neither gains nor loses energy.